Section 5.2, Data Persistence with Spring Data JDBC. Spring supports a wide variety of data persistence technologies through the Spring Data project, which contains specific modules dedicated to relational, JDBC, JPA, R2DBC, and non-relational databases, Cassandra, Redis, Neo4j, MongoDB, and so on. Spring Data provides common abstractions and patterns, making it straightforward to navigate the different modules. This section focuses on relational databases, but the key points of the interaction between an application using Spring Data and a database, shown in Figure 5.3, apply to all of them.
Figure 5.3. A driver configures the connection between the application and the database. Entities represent domain objects and can be stored and retrieved through a repository.
The main elements in the interaction shown in Figure 5.3 are database drivers, entities, and repositories. Database drivers. Components that provide integration with a specific database through connection factories. For relational databases, you can use a JDBC driver, Java Database Connectivity API, in imperative blocking applications, or an R2DBC driver in reactive/non-blocking applications. For non-relational databases, each vendor has its own dedicated solution. Entities, domain objects that are persisted in a database. They must contain a field to uniquely identify each instance, a primary key, and can use dedicated annotations to configure the mapping between Java objects and database entries. Repositories, the abstractions used for data storage and retrieval. Spring Data provides basic implementations, which are further extended by each module to provide features specific to the database in use. This section will show you how to use Spring Data JDBC to add data persistence to a Spring Boot application like Catalog Service. You'll configure a connection pool to interact with a PostgreSQL database through the JDBC driver, define entities to be persisted, use repositories to access data, and work with transactions. Figure 5.4 shows how the Polar Bookshop architecture will look by the end of this chapter.
Figure 5.4. The Catalog Service application uses a PostgreSQL database to persist book data.
Spring Data JDBC or Spring Data JPA? Spring Data offers two main options for integrating applications with a relational database over the JDBC driver: Spring Data JDBC and Spring Data JPA. How to choose between the two? As always, the answer is that it depends on your requirements and specific context. Spring Data JPA, see this link, is the most used module in the Spring Data project. It's based on the Java Persistence API, JPA, a standard specification included in Jakarta EE, previously known as Java EE. Hibernate is the most popular implementation. It's a robust and battle-tested object relational mapping, ORM, framework for managing data persistence in Java applications. Hibernate provides many useful features, but it's also a complex framework. If you're not aware of aspects like persistence context, lazy loading, dirty checking, or sessions, you might face issues that will be hard to debug without a sound familiarity with JPA and Hibernate. Once you know the framework better, you'll appreciate how much Spring Data JPA simplifies things and boosts your productivity. To learn more about JPA and Hibernate, you can check out High Performance Java Persistence and SQL by Vlad Mihalcea, vladmihalcea.com, and Java Persistence with Spring Data and Hibernate by Catalin Tudosi, Manning 2022. Spring Data JDBC, see this link, is a more recent addition to the Spring Data family. It integrates with relational databases following the domain-driven design, DDD, concepts like aggregates, aggregate roots, and repositories. It's lightweight, simpler, and an excellent choice for microservices where domains are usually defined as bounded contexts, another DDD concept. It gives developers more control over SQL queries and allows the use of immutable entities. Being a simpler alternative to Spring Data JPA, it's not a drop-in replacement for every scenario, since it doesn't provide all the features offered by JPA. I recommend learning both, considering your requirements, and then deciding which module suits the specific scenario better. I've chosen to cover Spring Data JDBC here for its good fit with cloud-native applications and its simplicity. Thanks to the Spring Data common abstractions and patterns, you can easily convert a project from Spring Data JDBC to Spring Data JPA. In the following sections, I'll point out the main differences between the two to give you enough information in case you want to try implementing the same requirements using Spring Data JPA. In the code repository accompanying the book, you'll also find a JPA version of Catalog Service you can use as a reference, Chapter 05/05N/Catalog Service JPA. Section 5.2.1, Connecting to a Database with JDBC. Let's start implementing the data persistence layer for the Catalog Service application. As a minimum, you'll need to import the Spring Data module for the specific database you want to use and, if required, also the database driver. Since Spring Data JDBC supports different relational databases, you'll need to explicitly declare a dependency on the specific database driver you want to use. You can add the two new dependencies to the build.gradle file for the Catalog Service project, Catalog Service. Remember to refresh or re-import the Gradle dependencies after the new addition.
Listing 5.1, Adding dependency for Spring Data JDBC in Catalog Service.
These are the main dependencies. Spring Data, JDBC, org.springframework.boot, Spring Boot Starter Data, JDBC, provides the necessary libraries to persist data in relational databases using Spring Data and JDBC. PostgreSQL, org.postgresql provides a JDBC driver that allows the application to connect to a PostgreSQL database. The PostgreSQL database is a backing service to the Catalog Service application. As such, it should be handled as an attached resource according to the 15-factor methodology. The attachment is done through resource binding, which in the case of PostgreSQL consists of the following: a URL to define which driver to use, where to find the database server, and which database to connect the application to. Username and password to establish a connection with the specified database. Thanks to Spring Boot, you can provide those values as configuration properties. This means you can easily replace the attached database by changing the values for the resource binding. Open the application.yml file for the Catalog Service project and add the properties for configuring the connection with PostgreSQL. Those values are the ones you defined earlier as environment variables when creating the PostgreSQL container.
Listing 5.2, Configuring the connection to a database using JDBC.
Opening and closing database connections are relatively expensive operations, so you don't want to do that every time your application accesses data. The solution is connection pooling. The application establishes several connections with the database and reuses them, rather than creating new ones for each data access operation. This is a considerable performance optimization. Spring Boot uses Hikari CP for connection pooling, and you can configure it from the application.yml file. You want to configure at least a connection timeout, spring.datasource.hikari.connection timeout, and a maximum number of connections in the pool, spring.datasource.hikari.maximum pool size, because these both affect application resilience and performance. As you saw for the Tomcat thread pool, multiple factors influence which values you should use. As a starting point, you can refer to the Hikari CP analysis of pool sizing. See this link.
Listing 5.3, Configuring the connection pool to interact with the database.
Now that you have connected a Spring Boot application to a PostgreSQL database, you can go ahead and define what data you want to persist. Section 5.2.2, Defining persistent entities with Spring Data. In Catalog Service, you already have a book record representing a domain entity for the application. Depending on the business domain and its complexity, you might want to distinguish the domain entity from the persistent entity, making the domain layer utterly independent of the persistence layer. If you'd like to explore how to model that scenario, I recommend referring to domain-driven design and hexagonal architecture principles. In this case, the business domain is quite simple, so we'll update the book record to also be a persistent entity. Making a domain class persistent. Spring Data JDBC encourages working with immutable entities. Using Java records to model entities is an excellent choice, since they're immutable by design and expose an all-args constructor that the framework can use to populate objects. A persistent entity must have a field that acts as the identifier for the object, which will translate to the primary key in the database. You can mark a field as an identifier with the ID annotation, from the org.springframework.data.annotation package. The database is responsible for generating a unique identifier for each created object automatically. Note: books are uniquely identified by an ISBN, which we can call a natural key, or business key, for the domain entity. We could decide to use it also as the primary key or introduce a technical key, or surrogate key. There are pros and cons to both approaches. I chose to use a technical key to make it easier to manage and to decouple domain concerns from persistence implementation details. That is enough to create and persist a book in the database. It's also okay when a single user updates an existing book object in isolation. But what happens if the same entity is updated by multiple users concurrently? Spring Data JDBC supports optimistic locking to address that concern. Users can read data concurrently. When a user attempts an update operation, the application checks if there has been any change since the last read. If there was, the operation is not performed, and an exception is thrown. The check is based on a numeric field that starts counting from 0 and automatically increases at every update operation. You can mark such a field with the version annotation from the org.springframework.data.annotation package. When the ID field is null and the version field is 0, Spring Data JDBC assumes it's a new object. Consequently, it relies on the database to generate an identifier when inserting the new row in the table. When values are provided, it expects to find the object in the database already and to update it. Let's go ahead and add 2 new fields to the book record for the identifier and the version number. Since both fields are populated and handled by Spring Data JDBC under the hood, using the all-args constructor might be too verbose for situations such as generating test data. For convenience, let's add a static factory method to the book record for building an object by passing only the business fields.
Listing 5.4. Defining identifier and version for book objects.
Note: Spring Data JPA works with mutating objects, so you can't use Java records. JPA entity classes must be marked with the entity annotation and expose a no-args constructor. JPA identifiers are annotated with ID and version from the javax.persistence package instead of org.springframework.data.annotation. After adding the new fields, we need to update a few classes using the book constructor, which now requires passing values for ID and version. The book service class contains the logic for updating books. Open it and change the edit book details method to ensure the book identifiers and versions are correctly passed along when calling the data layer.
Listing 5.5. Including existing identifier and version on book updates.
In Book Data Loader, we can use the new static factory method for building book objects. The framework will take care of handling the ID and version fields.
Listing 5.6. Using the static factory method when creating a book.
I'll leave it to you to update the auto test similarly. You can also extend the tests in the bookJSON-test class to verify the serialization and deserialization of the new fields. As a reference, you can check Chapter 05/05 Intermediate/Catalog Service in the code repository accompanying this book. As a persistent entity, the book record will be automatically mapped to relational resources. Class and field names are transformed into lowercase, and the camel case is translated into words joined by underscores. The book record will result in the book table, the title field will result in the title column, the price field will result in the price column, and so on. Figure 5.5 shows the mapping between the Java object and the relational table.
Figure 5.5. Java classes marked as persistent entities are automatically mapped by Spring Data JDBC to relational resources in the database.
Creating the database schema. The database must have a table defined, as shown in Figure 5.5, for the mapping to work. Spring Data offers a feature to initialize a data source at startup time. By default, you can use a schema.sql file to create a schema and a data.sql file to insert data in the newly created tables. Such files should be placed in the src/main/resources folder. That is a convenient feature, and it's useful for demos and experiments. However, it's too limited for use in production. As you'll see later in the chapter, it's better to create and evolve relational resources with a more sophisticated tool, like Flyway or Liquibase, which will let you version control your database. For now, we'll use the built-in database initialization mechanism so that we can focus on the data layer implementation first. Note: Hibernate, the foundation for Spring Data JPA, offers an interesting feature for automatically generating schemas from the entities defined in Java. Once again, this is convenient for demos and experiments, but please think twice before using it in production. In your catalog service project, add a new schema.sql file in the src/main/resources folder. Then write the SQL instructions to create the book table, which will be mapped to the book record in Java.
Listing 5.7. Defining the school instructions to create the book table.
By default, Spring Data loads the schema.sql file only when using an embedded in-memory database. Since we're using PostgreSQL, we need to enable the functionality explicitly. In the application.yml file for your catalog service project, add the following configuration to initialize the database schema from the schema.sql file.
Listing 5.8. Initializing the database schema from an SQL script.
At startup, Spring Data will read the file and execute the SQL instructions in the PostgreSQL database to create a new book table and make it possible to start inserting data. In the next section, you'll make it possible to capture audit events related to the persistent entities and keep track of when each row has been inserted into the table and modified most recently. Section 5.2.3. Enabling and configuring JDBC auditing. When persisting data, it's useful to know the creation date for each row in a table and the date when it was updated last. After securing an application with authentication and authorization, you can even register who created each entity and recently updated it. All of that is called database auditing. With Spring Data JDBC, you can enable auditing for all the persistent entities using the Enable JDBC Auditing annotation on a configuration class. In the com.polarbookshop.catalogservice.config package, add a data config class to gather JDBC-related configuration.
Listing 5.9. Enabling JDBC auditing via annotation configuration.
Note: in Spring Data JPA, you would use the Enable JPA Auditing annotation to enable JPA auditing, and you would annotate the entity class with entity listeners, auditing entity listener.class, to make it listen to audit events, which doesn't happen automatically, as in Spring Data JDBC. When this feature is enabled, audit events are generated whenever data is created, updated, or deleted. Spring Data provides convenient annotations, listed in Table 5.1, that we can use on dedicated fields to capture the information from such events, audit metadata, and store it in the database as part of the entity.
Table 5.1. When database auditing is enabled, these annotations can be used on entity fields to capture audit metadata. View table figure.
In Catalog Service, we can add the created date and last modified date fields to the book record. In Chapter 12, after introducing Spring Security, we'll extend this object to also capture who created or updated the entity. Open the book record, add the two new fields, and update the static factory method accordingly. They can be null when instantiating a new object because they will be populated by Spring Data under the hood.
Listing 5.10. Adding fields to store audit metadata in a persistent entity.
After extending the book record, the book service class needs to be updated one more time. Open it and change the edit book details method to ensure the audit metadata is correctly passed along when calling the data layer.
Listing 5.11. Including the existing audit metadata when updating a book.
Next, let's update the schema.sql file to add the columns for the new fields to the book table.
Listing 5.12. Adding columns for audit metadata to the book table.
I'll leave it to you to update the auto tests accordingly when necessary. You can also extend the tests in BookJSON tests to verify the serialization and deserialization of the new fields. As a reference, you can check Chapter 05/05 Intermediate/Catalog Service in the code repository accompanying this book. So far, you have got everything in place to map your Java objects to relational objects in a database, including audit metadata. You still need a way to access data from the database, though. That's the subject of the next section. Section 5.2.4. Data Repositories with Spring Data. The repository pattern provides an abstraction for accessing data independently of its source. The book repository interface used by Book Service is an example of a repository. The domain layer, which contains the business logic, doesn't need to know where the data comes from, as long as it gets access. In Chapter 3, we added an implementation of the repository interface to store data in memory. Now that we're building the persistence layer, we'll need a different implementation to access data from PostgreSQL. The good news is that we can use Spring Data repositories, a technical solution that provides access to data from a data store independently of the specific persistence technology used. It's one of the most valuable features of Spring Data, because we can use the same repository abstraction in any persistence scenario, whether relational or non-relational. Using a data repository. When using Spring Data repositories, your responsibility is limited to defining an interface. At startup time, Spring Data will generate an implementation for your interface on the fly. In the Catalog Service project, Catalog Service, go ahead and delete the in-memory book repository class. Let's now see how we can refactor the book repository interface from the Catalog Service project. First, it should extend one of the available repository interfaces provided by Spring Data. Most Spring Data modules add repository implementations specific to the data source supported. The Catalog Service application requires standard CRUD operations on book objects, so you can make the book repository interface extend from CRUD repository. CRUD repository provides methods to perform CRUD operations, including save and find all, so you can remove their explicit declarations from your interface. The default methods defined by CRUD repository for book objects are based on their ID annotated fields. Since the application needs to access books based on the ISBN, we must explicitly declare those operations.
Listing 5.13, Repository Interface for Accessing Books.
At startup time, Spring Data will provide an implementation for book repository with all the most common CRUD operations and the methods you declared in the interface. There are two main options for defining custom queries in Spring Data. Using the query annotation to provide an SQL-like statement that will be executed by the method. Defining query methods following a specific naming convention, as described in the official documentation. See this link. Generally, you can build a method name by combining multiple pieces, as described in Table 5.2. At the time of writing, Spring Data JDBC supports this option only for read operations. On the other hand, Spring Data JPA provides full support for it.
Table 5.2. You can add custom queries to a repository and have Spring Data generate implementations for you by following a specific naming convention comprising these building blocks. View table figure.
Using some of the methods provided by the CRUD repository interface and inherited by Book Repository, we can improve the Book Data Loader class so that we start with an empty database during development and create books with a single command.
Listing 5.14, Using Spring Data methods to delete and save books.
Defining transactional contexts. The repositories provided by Spring Data come configured with transactional context for all the operations. For example, all methods in CRUD repository are transactional. That means you can safely call the saveAll method, knowing that it will be executed in a transaction. When you add your own query methods, as you did for Book Repository, it's up to you to define which ones should be part of a transaction. You can rely on the declarative transaction management provided by the Spring Framework and use the @transactional annotation from the org.springframework.transaction.annotation package on classes or methods to ensure they are executed as part of a single unit of work. Among the custom methods you defined in Book Repository, delete by ISBN is a good candidate for being transactional, since it modifies the database state. You can ensure it runs in a transaction by applying the transactional annotation.
Listing 5.15, Defining transactional operations.
Note: for more information about the declarative transaction management provided by Spring Framework, you can refer to the official documentation. See this link. Great job! You successfully added data persistence capabilities to the Catalog Service application. Let's verify that it works correctly. First of all, make sure the PostgreSQL container is still running. If not, run it as described at the beginning of this chapter. Then start the application, /Gradle W boot run. Send HTTP requests to each REST endpoint and ensure it works as expected. When you're done, remove the database container, docker rm-fv polar postgres, and stop the application, Control-C. Tip: in the repository accompanying the book, you will find useful commands for querying the PostgreSQL database directly and verifying schemas and data generated by the application, Chapter 05/05 intermediate/catalog service/readme.md. Manual verification of data persistence is fine, but automated verification is better. That's what the next section is all about.